Okay, we're starting the Zoom meeting for Physics 231. We're in finishing the third week of the semester, and we're working on chapter 3. The reading quiz for chapter 3 is due at the end of today. Most people have already done it, or at least have done most of it. Here's the Zoom meeting. We're doing the Zoom meeting now. And the main problem set for chapter 3 is due Monday. That's problem set 2. Some people have already started problem set 2. Quite a few people have started it. Not very many people have finished it. There's an exam coming up, so I'll say a little bit about that at the end. But let's take a look at the equations from chapter 3. Chapter 3 is called Motion in Two Dimensions. And so you're going to need the equations from chapter 3. Here are some of them. Don't take these as all the equations from chapter 3. These are not really complete. Take notes when you read the chapter. The equations of kinematics we already studied last week for one dimension. So now we're just extending this into 2 dimensions. And one kind of problem which is important is the projectile, an object moving in Earth's gravity. And there, the 2 dimensions are horizontal, parallel to the surface of the Earth, and vertical, perpendicular to the surface of the Earth. So we'll call the vertical direction y, the horizontal direction x. Now, in the direction of x, there is no acceleration, unless aerodynamic forces happen to be important. But we usually, when we're concerned with projectiles, we usually neglect any kind of aerodynamic forces. So the only force is the force of gravity, which is vertical. So there is no horizontal force. So the equations for horizontal motion are just equations for constant velocity. X, as a function of time, is x0 plus v0x t, where t is the time, x0 is the initial x-coordinate at time 0, v0x is the initial velocity component in the x direction. Then y is a problem with constant acceleration. That's a problem we studied back in chapter 2. That's constant acceleration downward in the negative y direction equal to 9.81 meters per second squared, acceleration due to gravity. So then the equation for y, the y coordinate, is y0 plus v0y times t minus a half gt squared. This is plus 1/2 the acceleration times t squared. But the acceleration is negative. The acceleration is minus g. So projectile is one example of motion in 2 dimensions. It's really motion in 3 dimensions. But again, if the aerodynamic forces are negligible, then it's really just 1 dimension. The projectile just moves along a parabola. The acceleration is 0 in the x direction, the acceleration vector, is 0 in the x direction and negative g in the y direction. The velocity will be constant in the x direction, so it'll just be v0x, and then linearly decreasing in the y direction, v0y minus gt. So if the projectile is moving upward, then this says that the upward velocity is decreasing. On the other hand, if the velocity is downward, the projectile is moving downward, then the downward component of velocity is negative, and it's increasing in absolute value. So the projectile, whatever it is moving faster in the downward direction if it's moving downward. But it may be moving upward, it may be moving downward. You know, velocity is a vector, so the components of velocity can be positive or negative. Okay, so these are equations we know from last week. And it's just that we have to put them together to describe the motion of a single object in 2 dimensions. The initial velocity vector will have some magnitude, that's v0, and some direction. We usually measure the direction relative to the horizontal, so that would be the normal direction. I mean, that would be the direction which we usually use. Call it theta. So then v0 in the x direction, if I look at this little right triangle, the x direction is the direction adjacent to the angle. So v0 in the x direction is v0 cosine theta. And v0 in the y direction, the initial vertical direction, is v0 sine theta. Because again, if I look at this little right triangle here, the opposite to the angle theta is the vertical part of the triangle. So these are the main equations that you need for a problem with a projectile. Now again, these may not be complete. So when you read chapter 3, make sure you take your own notes so that you end up with a complete set of equations. Another important equation that is not written down here, for example, is the range of a projectile. You'll find that in one of the problems, problem 100, at the end of the chapter. It gives a range formula. A range formula is often useful. You might want to have that written down in your notebook for when you take the exam. The other kind of problem which is important in chapter 3 is circular motion. Now, projectile motion is easy because the vertical component and the horizontal component sort of separate. You see the vertical components, x and vx, sort of separate from, the horizontal component sort of separates from the vertical component. So you sort of have an equation for x, an equation for y, and they don't really refer to each other unless you're dealing with the angle. And then you have to use the trigonometric relations. And then, in fact, x and y will refer to each other. But for the time dependence, as far as the time dependence is concerned, you sort of have 2 one-dimensional problems, which go together to make a 2-dimensional problem. But circular motion is different. Circular motion, you have an object moving on a circle. This might be a horizontal circle. So here the coordinates x and y might be north and east. Well, we would usually call this the x direction, so that's east. And we would usually call this the y direction, and that's north. And so the circle is on the surface of the earth. It's horizontal. Or this could be a vertical circle, in which case x would be in some horizontal direction and y would be in the vertical direction. It wouldn't be a projectile because the projectile is only got one force, and the trajectory is necessarily a parabola. That was discovered by the great Galileo. But you could have an object which is moving around in a vertical circle. It wouldn't be described by these equations, because these equations are only when you have the constant acceleration. This would have a variable acceleration. Now, what is the acceleration when you have vertical motion? Sorry, when you have circular motion. It's probably easiest if you think of this as a circle on the surface of the earth, something horizontal. The velocity is always tangent to the circle because velocity is the rate of change of position. So if the position changes from here to here, a very small time later, you see the direction of motion, it's tangent to the circle. The velocity is the rate of change of position. So velocity is tangential. Now, what about acceleration? Well, acceleration could be towards the center. In fact, if the speed is constant, which is often a problem we consider, if the speed is constant, that's called uniform circular motion. So it's moving, think of this as a race car going around a racetrack. It has a constant speed, say 60 miles an hour or something. That's uniform circular motion. Well, then its acceleration is this way. Toward the center of the circle is the acceleration. We use the word centripetal to describe the direction towards the center of a circle. Centripetal is just a fancy Latin type of word, which means towards the center of the circle. So that's the direction. If the velocity is tangent, the acceleration is perpendicular to the velocity. It's centripetal. Well, that's the direction. What about the magnitude? Because A is a vector. What's the magnitude? Well, it's v squared over r is the magnitude. Negative v squared over r is the acceleration in the radial direction. The radial direction means pointing away from the center. So this is the unit vector in the radial direction, or this away from the center. But the acceleration is toward the center. So the acceleration is negative. The acceleration component in the radial direction is negative. And the magnitude is v squared divided by r. R is the radius of the circle. V is the speed, and I'm only talking about uniform circular motion here. So this is only the case where v is a constant. So when an object moves around in a circle with a constant speed, it has an acceleration. But the acceleration is perpendicular to the velocity vector. So the velocity magnitude doesn't change. The velocity magnitude doesn't change, but the velocity direction is changing. And when there's a change in velocity, there's an acceleration. The acceleration is the rate of change of velocity. So there's a centripetal acceleration in uniform circular motion. So that's one equation you'll need to know, v squared divided by r. And the other equation you need to know is how to relate the period of revolution around the circle. How long does it take to go from this point all the way around the circle back to this point? That's called the period. That's the period of revolution. And period is a time. It's the time it takes to go once around the circle. Speed is the rate of change of distance. So the distance over the speed is the time. And for one complete period, the distance is one circumference. The circumference of a circle is 2 pi r. So, to solve problems involving uniform circular motion, you have to know these two equations. How to relate the acceleration and the velocity, how to relate the period and the velocity. Of course, r, the radial coordinate, is a constant for a circle. R is just this capital R. All right, so those are the equations and the ideas you take away from chapter 3. Here's again another visualization of uniform circular motion. If you have an object, this little black dot, moving on a circle with a constant speed means uniform. You can also have the object moving faster as it goes around the circle. Think of a race car. If the race car is just moving at a constant speed, well, that's uniform circular motion. But suppose the driver puts on the brakes. Well, then the speed will decrease. That's not uniform circular motion. Or what if the driver pushes down on the accelerator pedal? Well, then the speed will increase. And that's not uniform circular motion. But just remember, for uniform circular motion, the velocity vectors are always tangent to the circle. The acceleration vector is always toward the center of the circle. And you can sort of see why the direction is in that way if you look at this picture. You have a velocity going this way. A little later, you have a velocity going this way. How did the velocity change? Well, it changed from this, at this point, to this. At this point. So here's the velocity right now. Here's the velocity a little later. Now, if I compare these two vectors and I ask, how do the vectors change? Well, the change is in this direction. That's towards the center. If I move these 2 points very close together, then this acceleration vector will be right towards the center. So, here we have V1, here we have V2, here we have delta V, change of velocity, and the acceleration is the rate of change of velocity. So the average acceleration over this period of time will be in this direction. But if I make that a very small change in time, it'll be right towards the center of the circle. And the equation, first published by the Dutch physicist but also known to Newton. Newton understood this. Maybe Newton learned this from reading something that was published by Huygens. Huygens was a Dutch physicist who first published a description of circular motion. Maybe Newton knew this from reading Huygens, or maybe Newton just figured it out himself. Acceleration vector is negative v squared over r. The magnitude is v squared over r, times r hat. R hat is the unit vector away from the center. Negative r hat is towards the center. All right, so let's see if there are any questions. There's a question on the chat. Is the centripetal acceleration going to be constant even if the magnitude of velocity is constant, since the direction continues to change in the circular orbit? Yes, the centripetal acceleration, well, the acceleration vector changes. So you see how the velocity vector is constantly changing. As you go around the circle, it's constantly changing in direction. It's always tangent to the circle, but everywhere along the circle, that's in a different direction. So the velocity vector is constantly changing. That means there's an acceleration at every point on the circle, and the acceleration vector is constantly changing. At every point, it's towards the center, but that's in a different direction for different points. So the acceleration vector is constantly changing. But the acceleration magnitude doesn't change at all. The magnitude of the acceleration is v squared over r. And so if the speed is constant, the strength of the acceleration is constant, or the size of the acceleration is constant. It's always v squared over r. All right, so you have to be careful in chapter 3 to treat everything as a vector. You know, I say here, the velocity changes. Yeah, the velocity vector changes. The magnitude of the velocity vector doesn't change. We call that speed. So in uniform circular motion, the speed is constant, but the velocity is constantly changing. Not that the magnitude is changing, but that the direction is changing. And same way, the acceleration direction is constantly changing as you go around the circle, but the acceleration size is always v squared over r in that direction. All right, here's an example of a problem from the chapter. It's problem 36. This is on the homework assignment, which is due next Monday. It's illustrating vectors. It's called Take a Walk. Suppose you walk some distance d1 towards the east, and then a distance d2 in the direction of southwest in a time t. Then what's your final position? In other words, what's your final distance from the starting point? And what's your average velocity? So you have to be a little careful to distinguish between vectors and scalars. Distance is a scalar. Velocity is a vector. So we always do these problems in the same way. The first thing we do is draw a picture. So start by drawing a picture. You start at some point, you walk east, that's the x direction, by a distance d1. So now you're at the position d1, 0. And then you walk southwest. Well, this is southwest for a distance d2. This is a distance d2. So now you'll be at a position x final, y final, where x is the eastern coordinate and y is the northern coordinate. And now you want to know, what's the distance? Well, this is the distance. What's the distance from where you started? This is the distance from where you started. So that's the answer to problem A. And problem B is, what's your average velocity? Well, average velocity, we discussed average velocity last semester. It's the change in the position divided by the change in time. Now, the change in time is the time t that you were walking. So the average velocity will be the change in x. X is a vector, so it'll have two components. And then you divide by the time t that you were walking. So what are xf and yf? Well, xf will be the change in the x coordinate divided by t. Sorry, that's VXF. And VYF is the change in the y coordinate, that's this, divided by t. And the distance from where you started, the distance, the origin is where you started, the distance from the origin is the square root of xf squared plus yf squared by the Pythagorean theorem. So you have this picture, you have an xy coordinate system, you have a horizontal distance xf, you have a vertical distance minus yf, which is negative, it's in the south direction. So xf is d minus d2 cosine of 45 degrees. d1 minus d2 cosine of 45 degrees. This is 45 degrees because the direction is southwest. And yf is started at 0. At this point, it's still 0, but now it's going negative d2 sine of yf. So if I look at this little right triangle, put it in a different color, this little right triangle, the hypotenuse is d2, the x component is negative d2 cosine of 45 degrees, the y component is negative d2 sine 45 degrees. Cosine of 45 degrees and sine of 45 degrees are both equal. They're both 1 over the square root of 2. So here's xf and yf. In terms of the given values of d1 and d2. And the final distance is just this squared plus this squared. And as for the velocity, well, it's just the final distance, the final displacement, I should say. It's the x displacement divided by t. And the other component is the y displacement divided by t. So see, the answer to part B will have two numbers. The answer to part B has two parts. There's xf over t and yf over t. But the trigonometry comes in figuring out xf and yf. All right, so that's a little exercise using vectors and using trigonometry. That's not really very difficult, but it involves motion in 2 dimensions. Here's another problem from problem set 2. I don't think this one's in the book. It's called the geosynchronous satellite. A geosynchronous satellite revolves around the Earth on a circular orbit with some radius, that's given, a large radius, larger, quite a bit larger than the radius of the Earth, 6.63 times the radius of the Earth. So there are 2 radii here. There's capital R, which is the radius of the Earth, and there's little r, which is the radius of the orbit. Okay, so it's on a circular orbit with this radius r, and the period of revolution is 24 hours. That's why we call it geosynchronous, because if this is in the equator, then as the Earth rotates, the Earth rotates every 24 hours. If the Earth rotates in 24 hours and the satellite goes around the Earth in 24 hours, then the satellite will always be over the same position on the Earth. It'll be over the Earth's equator. It'll be somewhere perpendicular to the Earth's equator, and it'll always be in the same position as the Earth rotates. If the time to go all the way around is exactly the time to rotate, 24 hours. Then the question is, what's the acceleration? So Here's the velocity vector, which is constantly changing as the satellite goes around the orbit. And here's the acceleration vector, which is always towards the center of the Earth. In other words, it's constantly changing as the satellite goes around the Earth, so that it's always directed centripetal. So what's the magnitude of the acceleration? Well, the direction is towards the center of the Earth. What's the centripetal acceleration? Well, we have these equations. A is v squared over r. That's the centripetal acceleration magnitude. We have the other equation. V is 2 pi r over t. So if I want to know A, I take this squared, divide by r. I'll have r squared divided by r. There'll be r in the numerator. 2 pi squared is 4 pi squared in the numerator, and t squared in the denominator. So that's the first step in any physics problem, is to draw a picture. So here's the picture. And label it not with numbers, but with symbols. So in this case, we label the two radii. R, capital R, is one of the radii. Little r is the other radius. V is the speed. A is the acceleration. So I draw a picture and I label it. That's step one. Step two is to write down the necessary equations. Well, circular motion, v squared over r. And v is the circumference over the time. So there are the equations. Step three is a little bit of analysis, geometric or algebraic analysis of the equations. So you see, I sort of did this in my head. I took these two equations and I combined them into an equation for A, where the only variables are r and t, but those are both given. So that's step three. Now, step four is to put the numbers into the final equation. R is 6.63 times 6.37 times 10 to the 6 meters. T is 24 hours, which is 24 times 3,600 seconds per hour. So it's 86,400 seconds. So A is 4 pi squared. Well, pi squared is about 10, so let's call it 10. R, well, 6 times 6 would be 36. 7 times 7 would be 49. So this product will be about 42. And the power of 10 is 10 to the 6. And what about the unit? Well, the unit in this numerator is meters. And the denominator is 86,400 seconds. So that's like 8.6 times 10 to the 4th seconds. When you square that, you have 8.6 squared. That's about 75. Times 10 to the 4th squared is 10 to the 8th. And the unit. T has the units of s, so t squared is s squared. Now, the answer will be a number with a unit. Now, you can see what the unit is. It's meters in the numerator, seconds squared in the denominator. So it's meters per second squared, which is appropriate for acceleration. And now what about the number? Well, 42 over 75 is about 1 over 2. 4 divided by 2 is about 2. The rest is powers of 10. 10 times 10 to the 6th would be 10 to the 7th, divided by 10 to the 8th is 10 to the minus 1. So it's about 0.2 meters per second squared. Now, of course, you'll want to do this with your calculator. And a little more accurately. This isn't accurate enough for ln kappa. So you do the calculation accurately with your calculator, but you notice you don't even pick up your calculator until you've analyzed the problem. You don't think in terms of numbers. You think in terms of variables. Now there's part B, Newton's famous calculation. Newton showed that this acceleration is roughly g the acceleration on the Earth's surface times r squared over r squared. And that's one of the ways that Newton showed that the acceleration, that the force of gravity decreases as 1 over the distance squared. So this was when Newton was a very young man and still just working on the theories of motion and gravity. He came to the conclusion that the force of gravity goes like 1 over the distance squared from this calculation. Here's another problem from the homework assignment. It's in the assignment, it's just called additional problem. Is that the one I want? There was the geosynchronous satellite. Oh no, that's not Newton's famous calculation. That's the geosynchronous satellite. Now we come to a famous calculation. I see. So I had that wrong. This is the famous calculation. That had to do with the acceleration of the moon around the Earth. So ignore what I said here. That was wrong. I was looking at the other slide. All right, so again, this is a problem in the assignment for Monday. It says the moon orbits the Earth in 27.3 days. The orbital radius is about 384,000 kilometers. Then what's the centripetal acceleration? That's part A. Well, this is just like the other problem. The centripetal acceleration will be v squared over r, and v will be 2 pi r over t. So the analysis of the part A of the problem is just like the problem we just did. Here's the picture. We start by drawing a picture. Here's the picture. Here's the moon revolving around the Earth. And the distance is r, and that's given. 384,000 kilometers. And the time to go around once around the circumference is given. That's 27.3 days. There's a velocity tangent to the circle. There's an acceleration toward the center of the circle. So that's the picture. Now we write down the equations. Well, it's the same equations as last time, because this is, again, a problem with uniform circular motion. A is v squared over r. V is 2 pi r over t. Now, some of the quantities here are known. We might as well start writing down what quantities are known. T is 27.3 days, but you'll want to convert that to seconds. R is 384,000 kilometers, but you'll want to convert that to meters. So that's 384 million meters, or 3.84 times 10 to the 8th meters. And now A will be 2 pi squared r over t squared by comparing these two. So there's the algebra. And now the numerator will be some number times meters. The denominator will be some number times seconds squared. So the answer will be a number, which will be C1 over C2 squared, times a unit, which will be MC squared, meter per second squared. So again, the unit is meter per second squared, the unit of acceleration. And the number will be 27.3 times the number of seconds in a day. That's C1, divided by 3.84 times 10 to the 8th. That's the number for, no, I had that wrong. It'll be 2 pi r, where r is this number, That'll be the numerator, divided by t squared. T squared will be 27.3 days times the number of seconds in a day. So that'll be t squared. And that's where you need to pick up your calculator. So the last step in any of these Kappa homework problems is to pick up your calculator. But first you analyze the problem. All right, now here's where Newton's famous calculation comes in. Newton showed that this acceleration, which he could calculate from 27.3 days and 384,000 kilometers, is the same as the acceleration due to gravity on the Earth times the ratio of distances to the center of the Earth, showing that the acceleration due to gravity, or really it's the force of gravity, is proportional to 1 over the distance squared. All right, now the final question. The final question was called additional problem. I don't think it's in the book. It shows here somebody kicks a soccer ball from the top of one building. It's a projectile. So it travels along a parabolic path and it lands on the top of another building. And the information that you're given is the height of the first building, 28 meters, and the height of the second building, 10 meters. So we'll call that H prime is the first building, and H is the second building. And you're also told information about the speed and angle of the projectile. So the initial speed, so here's the initial velocity vector. It's a vector. So it has a magnitude, that's the speed, and a direction. And the direction is measured relative to the horizontal. So the first step is to draw a picture with labels. Well, we already have one picture, but this picture doesn't show everything. It'd be better to draw a better picture. So draw a better picture. Set up a coordinate system. Y is vertical, X is horizontal. It starts out, let's say at X equals 0. So let's define this to be the origin. It starts out at X equals 0 and Y equals H prime. That would be the height. Then it follows a parabolic trajectory after it's been kicked. And it lands on the other roof. So it lands at Y equals H. That's given. And what you want to calculate is how far. What are we trying to calculate? What's the horizontal distance traveled? So this is the unknown. That's what we're trying to calculate. So the first step in a physics problem is to draw a picture which labels, not with numbers, but with variables, symbols, the problem. So this shows the trajectory. The second step is to write down the necessary equations. Well, it's a projectile. So we'll write down equations for projectile motion. Remember, the horizontal motion is just constant velocity. So x at time t is x0. Well, that's 0 because we took the initial position of the ball to be the origin, plus v0 xt. That's the velocity in the x direction times the time. Now, I don't know the time. That's something I'll have to figure out. But here's one of the equations I'm going to need, the horizontal coordinate. And the other one will be the vertical coordinate, which is y0 plus v0 yt plus 1/2 ayt squared. Well, ay is minus g. Y0 is h prime. So y0 is h prime, x0 is 0. Now v0x is v0 cosine theta, because if I draw a little picture, a little triangle here for the velocity vector, I have this little right triangle. And here's the angle theta. So there's the angle theta, which is given in the problem. And x is adjacent to theta. So the x component will be the hypotenuse v0 cosine theta. And y is the opposite to the angle theta. So the y component will be the hypotenuse v0 times the sine of theta, using trigonometry. Cosine is the side adjacent to the angle, sine is the side opposite to the angle. So that's step 2, is to write down the equations. Now, step 3 is to use algebra. What I have here is 2 equations with 2 unknowns. What are the unknowns? The unknowns are t, the time when the ball hits the roof, the second roof, and r, the distance that it's traveled. So I have 2 unknowns, I better have 2 equations. And now what I'm looking for is r. So if I think of x, if I think as t as the time when it hits the other equation, then x at time t is r. And x0 is 0, and v0x is v0 cosine theta times t. So that's an equation for the horizontal distance when the ball hits the second roof. But I don't know what t is, so I need another equation. And that's where I use the vertical part. If I say t is the time when it hits the roof, then y is h. So I put y equals h, y0 is h prime, v0y, v0 sine theta t, minus half gt squared. So this gives me an equation for r, which is the unknown. This gives me an equation in which the only unknown is t. So I can solve this equation for t. Now, it's a quadratic equation, so it's going to require solving a quadratic equation. But remember, you learned how to solve quadratic equations back in algebra. So this is a little bit of algebra. Solve this equation for t. Then once you know t, put t back in this equation. V0 is given, theta is given, you can calculate r. So first solve the second equation for t, and then put that into the first equation to calculate r. That's where you need your calculator. Not quite done with algebra, because you got to write down the quadratic formula for t. So you write down the quadratic formula for t, then you pick up your calculator to calculate the numerical value of t. Then you use your calculator again to calculate the numerical value of r. So let's see. Any questions about the calculations for today? You can either type it in the chat or just unmute your microphone and speak up. Okay, then. Problem set 2, that's the problems for chapter 3, is due Monday. So some people have already done some of them. You can work on them during the weekend and all day Monday, but don't leave them all till Monday. I mean, do a few each day. So do some more Saturday and do some more Sunday and finish them up on Monday. Don't try to do them all on Monday because it's a long assignment. Also, you should have a study group. You should try to find some other students taking the class who are either living in the nearby where you live, or maybe have the same major. Maybe there are students who are taking other classes which you're taking. You know, if you're a packaging major, you might know a student who's majoring in packaging and taking this course. You can contact other students at the GroupMe site if you don't know anybody else. And finally, if you get stuck on a problem, submit a question to the discussion board. If you're working on a problem, you can't quite figure out what it is, what to do on it. There are hints for most of the problems. So if you're stuck, you should probably take a peek at the hints. But if after reading the hint, you still don't quite know what you're supposed to do, or if you think there's something wrong with the problem, formulate a question about the problem and submit it to the discussion board. Probably somebody will answer your question. But don't do that late Monday night because then nobody's looking. I mean, everybody will have already finished the problem. So the discussion board is not very useful late Monday night, but you could submit the problems now or anytime until late Monday night, and then watch the board for answers to the question. Now, as I say, there's an exam coming up. So this wouldn't be too early to start thinking about exam 1. There'll be one more chapter. Exam 1 will cover chapters 2, 3, and 4. Well, 2 we've done, 3 you're working on now, be done Monday, and then there's chapter 4. Now, chapter 4 is probably the most difficult chapter in the book. And the assignments for chapter 4 will be long because that's a very difficult topic. Chapter 4 is on physics. Chapters 2 and 3 are just on math. You know, chapters 2 or 3 are just on kinematics. We haven't introduced any ideas of physics, just ideas of motion. But in chapter 4, we start studying physics, and in particular, forces and Newton's laws of motion, how motion is affected by forces. That's a difficult subject. That's why it took a great genius like Newton to figure it out. So chapter 4 will be more difficult than chapters 2 or 3. And then after chapter 4, the next day is exam 1. So start thinking about exam 1. And in particular, there are instructions for exam 1, which, well, I'm not sure if they're on Lon Kappa yet, but if you click on the site on Lon Kappa, you should get some instructions for exam 1. I'll make sure that they're put on the Lon Kappa course. Oh, here's another problem. I was going to talk about that, but we're already pretty much done with the hour. So any questions, any further questions? I don't see any questions on the meeting, on the chat. And I don't hear anybody asking a question. So I will stop the recording.